Hi, this is Xiping. So before I start, I would like to thank the organizers for organizing this very nice workshop online. And I also would like to thank Professor Maria Russ for inviting me to give this talk. Today I'm going to talk about the local abstractions of reflective group objects. So before we start, first let's review the theory of local abstractions. So we consider the field to be an algebraic closed field of characteristic 0, and we consider projective varieties. So we define the Nash blob of X to be the closure of the image of the Gauss map. So basically you take a smooth point of X and you map it to the pair of X with a tangent bundle. The closure is taken inside the Grassmannian bundle of the tangent bundle of Pn, and this closure is called the Nash blob. The universal bundle of the Grassmannian restricts to a vector bundle on X hat, and you can see that this actually extends the tangent bundle along the smooth part of X. So we will denote the projection by mu, this is a bidirectional map. And for any point P in X, we define the local abstraction of X at P to be the integration along the fiber of the Chern class of this Nash tangent bundle with the Segre class. This definition was actually due to Gonzalez, Springberg, and Verdeel, and they extend the original definition by McPherson to arbitrary algebraic closed field. So over complex numbers, McPherson originally defined the local abstractions to be the abstraction to extend the holomorphic distance one form. So after you pull back to the Nash blob and you extend from the boundary to the center. And later, for complex varieties, it was proved by Brzezinski, Davison, and Kashiwara that McPherson's local abstractions actually they are equivalent to Kashiwara's local Euler characteristics defined in his D-module theory. So by their index theorem, the local abstractions are closely related with the microlocal indices and the stock Euler characteristic of constructible sheaves. And by the work of Gaffney and Tessier, you can see that the local abstractions are actually related with the polar multiplicities. And also Brasselet's work has shown that the local abstractions are equivalent to the indices of conical vector fields. And in algebraic statistics, they have proved that you can use maximum likelihood degrees to compute the local abstractions. And in geometric representation theory, actually, the local abstractions are key ingredients in the study of the Cartan-Lustig polynomials. So from both singularity theory and the geometric representation theory of angle, the local abstractions, they are very important objects to study. So the goal of this talk is first, we're going to propose an algorithm to compute the local abstractions for what we will call the reflective linear group objects. And our algorithm depends on knowledge of the Chern-Schwarz-McPherson classes, which was first defined by McPherson, and then generalized to arbitrary field by Kennedy. So for such objects, the Chern classes actually can be computed from either representation theory angle, if you follow the work by Feher, Riemann, Valchenko, and Weber, or you can use the canonical intersection theory tool, which you take a resolution and then you compute a push up or push down. So as an application, we consider a very special type of reflective group objects, the naturally rank loci. There are actually three types of them: the ordinary case, the skew symmetric case, and the symmetric case. For all the cases, we give explicit formulas for the local abstractions. Actually, for such objects, you can see that we will mention they have the so-called local normal slice properties, which means that actually we don't really need to know all the information about the Chern classes. We only need to know their evaluations in 91, which we will define as the SM invariants. Okay. So first, let's review the theory of Chern classes. So we consider projective varieties X, and by a constructive function X, we mean a finite sum of the weighted sum of the indicator functions along closed subvarieties. So the the coefficients are integers, and we take the abelian group of constructive functions to be denoted by fx. And despite the standard basis, which are the indicator function along all the closed subvarieties, McPherson proved that if you take the Euler abstraction function on the closed subvarieties, this also forms a basis for the constructive function group. And he also defined the push forward. So for proper map f from x to y, you define the push forward of the constructive function to be you compute the Euler characteristic of the pullback or the fibers. So after this definition, he actually made the constructive function group into a functor. It's a functor from the category of projective varieties with proper morphism to the category of abelian groups. So we can compare this functor with the Char group functor. So the following theorem was originally proved by McPherson over complex number field using homology groups, and then generalized to arbitrary algebraic closed field of characteristic 0 by Kennedy. So the theorem says that there exists a unique natural transform, which we denote by C star, from the constructive group functor F to the child group functor A, such that for smooth varieties, the push forward the functor C star will take indicator function of X to the total Chern class of X. So notice that even though X is quasi-projective is not closed, the indicator function X 1X is actually also still a constructive function in the projective space. So we define the Chern-Schwarz-Malfern class of X to be the image of the indicator function 1X after the C star transform. So since the child group of Pn is actually a polynomial ring, the Chern-Schwarz-Malfern class of projective varieties also can be viewed as polynomials in the hyperplane class H. And if you take the substitution by H by 0, you can see that this actually computes the dimension 0 pieces of the Chern-Schwarz-Malfern class, which is the integration of such class over Pn, and by the definition of push forward of constructive functions, this equals the Euler characteristic of X. So this can be viewed as a singular version of the Poincare-Hopf theorem for smooth manifold. And we are actually interested in the polynomial valuation at negative 1. So for projective variety X, and we consider the fine cone sigma, we define SM invariant of X or sigma to be the signed evaluation of the Chern-Schwarz-Malfern polynomial at negative 1. So actually, when the base field is complex numbers, we prove that the SM invariance of sigma actually equals to Euler characteristic of the link space. So here the link space means that you take sigma, which contains 0, and you take a small ball centered at 0, and you cut it by a generic linear form, which you perturb it a little bit away from 0. The space is called the link space of sigma to 0, and the Euler characteristics are called the local Euler characteristics defined by Kashwara. So we prove that our SM invariants actually agree with such Euler characteristics for complex number field. And thus, we prove an algebraic version of the Brasselet-Le-Siet formula. So for stratified projective variety, and we take the stratification to be Si, and let Vi to be the fine cones. So the Euler characteristic, the local obstruction of the fine cone sigma at 0 equals to the weighted sum of the local obstructions of sigma at each strata, and the weighted sum are given by SM invariance. Okay. So now, after the preliminary, we are going to talk about the main object we are going to study here. So we consider linear algebraic group, actually wanted that to be connected, and we consider its representation V of a finite dimension. So we assume that among all the objects, which possibly be infinite, there is a maximum flag. This is a finite flag of objects. So by maximum means that you cannot put in more objects satisfying the following properties. And we label them in a way such that, so first, we want objects to be K-star invariant, so which means we want them to pass down to projective spaces. And then we want to label them by size. So for any j smaller than I, we want Oj to live outside of closure Oi. So this forces the OS to be the 1 point stratum 0. So also we want the closure of O1 to be the union of all the other obvious OIs. So the fourth property actually is where the name reflector comes from. We want the objects to be due to each other, which means that we want, after you take projectivization, we want the closure of OI to be projectivized due to closure of OS minus I. So, and the fifth condition is a technical condition in the algorithm. We want all the objects to be irreducible and of different dimensions. Okay, because if you allow objects of the same dimensions, that the algorithm might fail in the setting. Okay. So the algorithm is based on the following proposition. So basically it says that if we know the Chern-Schwarz-Malfern class of all the objects of such reflective group objects, and then we can compute the local obstruction from the Chern-Schwarz-Malfern classes. So we define Si to be the projectivized objects of Oi, and we define this A and H to be the Chern-Schwarz-Malfern class of Pn, the projective space. So for any object OR, assume that there are sets of integers alpha k and beta I such that the following equality hold. Okay, let's briefly explain the equality here. So on the left-hand side, the summation over all the objects Sk so that might live in the closure of the orbit Sr. And on the right side, the summation over all the objects Si such that it might live in the closure of the dual variety as S minus R. So the integers are treated as weights. Sorry. And then on the left side, the parenthesis is actually defined by Aloufei's projective duality. So Aloufei proves that the such duality actually interchanges the chain method class from a variety X to its dual varieties. So, and actually from his result, one can see that the local obstructions of the objects SR and objects SS minus R to dual objects, they of course satisfy this equality here. So by a linear system here, we mean that, notice this is actually equality of polynomials. So if you look at the coefficient of H, this gives you a linear system. And we actually prove that the solution space of this linear system is actually of dimension 2. So if you allow the initial values of this FR to equal to the beta F minus R to be 1, then these all obstructions are actually the only solution here. So based on this proposition, we can formulate the following algorithm. So first, we projectivize all the objects to projective space, and then we compute the Chen-Schwarz-Meffin class of it. And then for each R, we set up the following system of linear equations, which comes from the above proposition. So we set up such equality of the linear system for each object. Okay. And then the proposition says that the unique solution here are the local obstructions of the object SR and its dual object SS minus R. And since when we take projectivization, we actually forget about the 1-point strata 0, and we need to recover that. So we use the Brasselet-Le-Set formula to recover that. The local obstruction of the affine orbit OR at 0 actually is the weighted sum using our SM invariance. And the SM invariance are defined by the Chen-Schwarz-Meffin class evaluate 91. So we get everything back. Okay. So this is the algorithm. So the first remark is that this algorithm actually applies to general projective varieties, as long as that the objects, the stratification of objects of V of X and its dual variety X dual, they are all of different dimensions. And this algorithm will actually work for all the cases. And we mentioned here that recently there's a similar algorithm of Schubert cells, and proposed by Mihalcea and Zhang. They also use the Chen-Schwarz-Meffin class to give an algorithm to compute the local obstruction for Schubert cells in cosmic spaces. And since that Fechner, Riemann, and Weber, they give a way to obtain the Chen-Schwarz-Meffin classes of such group objects from representation theory angle. So actually our algorithm builds a bridge from the geometric representation theory to the study of singularities of such group objects, which we find to be quite interesting here. Okay. So this is our algorithm, and then we are going to apply our algorithm to the matrix rank loci. So we consider the space of matrices of 3 types: ordinary type, symmetric type, and skew symmetric types, and we will denote them by Mn, Mns, and Mn wedge. So we are going to use the subscript nk to mean the size n and of co-rank k. And they form stratifications for the matrix spaces, and prove by Eisenberg that the objects are irreducible and reduced, and they are of different dimensions. So the key point is the third property here, the normal slice properties, which means that if you take the size n and co-rank k matrices, and you take a normal slice at a point, you will get the normal slice to be isomorphic to the size r and the co-rank r minus k matrices. So this actually tells you that the local obstructions of a bigger size matrix at the strata is actually equal to the local obstruction of a smaller size matrix. So this reduces the number of variables from the previous algorithm, and thus we can use less information to obtain that, as we will see later. And the fourth property is key to our computation here. The projectivized rank loci, they have canonical resolution called the Turner transforms, which are isomorphic to the projective bundles of Grassmannians. So for the ordinary case, they are isomorphic to the projectivized of Q due to the nth power. For the skew symmetric case, it's a wedge square, and for the symmetric case, it's the symmetry product. Okay. So, okay, we are going to define the following child classes, and if you work with complex settings, they are actually cohomology classes. So we let the S and Q to be the universal sub and cosine bundles, and so for ordinary case, we define the T class. So here D is any integers. This is the variable here at the change. N and R denotes the size and co-rank. So this is a product of following tautological classes. By tautological classes, we mean the Chen class of tautological bundles. And for the wedge product and for the symmetric product, we actually define similar terms. But due to the computation, we need to add the following tails, the following here and the following here, and which in computation that it will give us a lot of trouble. Okay, and we will see later. So based on the definition of these determinant of child classes, we define the following Q polynomials. So they are defined in the same format. You integrate over the Grassmannian of the Chern class of the tangent bundle, and then you cut product with the following cohomological classes. So we define the polynomials by the evaluations at each integer d. And the reason that they are actually polynomial is actually because they are the push forward of the Chern-Schwarz classes of the Torino transforms. And here the error terms are due to computational issue. So actually, if you look at the form of the ordinary case, you can see that the determinant of child class here is purely symmetric. So which means that if you apply Olufe's projective duality involution, you substitute d by 91 minus d, and then you subtract this error term, you will get the Q polynomials for the correct n minus r rank loci. So this actually proves that by our algorithm, because this is actually involution of the Chern method classes, they actually prove that the Q polynomials for ordinary case are exactly the Chern method classes. So which means that you can directly compute a local obstruction. This is because that the Torino transform for ordinary case is actually a small resolution in McPherson's sense, and the incident cohomology shift convex is reducible, so it's a standard result. But unfortunately, we don't have such result for symmetric case and skew symmetric, because the tail here actually it loses symmetry property. As you see that if you substitute d by 91 minus d, you'll get a lot of other terms, which means you cannot cancel them easily. Okay. So now let's compute local obstruction of such rank loci. So first we mention here that to compute the local obstruction of the 3 types symmetric rank loci, it is actually equivalent to compute the SM invariance of them. So this is because the normal slice property. The normal slice property says that if you want to compute the local obstruction of a bigger size matrix, it is enough to compute the local obstruction of the smaller size matrix. And this reduces the number of variables a lot, so which means we don't need to know all the information about Chern-Schwarz classes. We only need to know the evaluations at 91, which are the SM invariants. And then the second proposition says that if you want to know SM invariance, then since it's a linear combination of the Q polynomials, you just need to know the evaluation of Q polynomials at 91. Okay, and the evaluations by the definition of Q polynomials, they are just integration of the tautological classes or Grassmannians. So we compute them. The results are given by the following. For ordinary case, just Newton polynomials and Newton binomials, and for the symmetric case, skew symmetrics, they are quite complicated. An interesting thing here we want to mention here is that we actually don't know how to directly prove them from Schubert calculus. So our proof is the following. So first we prove that the corresponding integrations actually equals to the Euler characteristic of the final scheme of linear spaces over certain generic conjecture hypersurfaces. And then we compute the Euler characteristic of such final schemes from geometrical point of view, and we use a reduction formula, and we take some geometric method to compute them out. We don't know how to direct compute them from Schubert calculus. And because of symmetry in the Q polynomials, actually we believe that a direct Schubert calculus computation would actually help us to understand the relation of the determinant of varieties to the Schubert cells. Okay. All right, so this is the result on the Q polynomials. So then we can know the SM invariance, and at last we can compute the local obstructions. For ordinary case, it was originally computed by Gaffney, Garuha, and Russ in 2018 for complex net field, and by myself for arbitrary algebraic closed field of whatever characteristic. And then for skew symmetric matrix, it was proved by Riemannian and his student Promptapan in his PhD thesis, and that the local obstruction are actually Newton's binomials. And for the symmetric case, I think this is still unknown, so we compute them out. The local obstruction of skew symmetric rank loci are also Newton binomials, but you can see that there is a vanishing here of the even size and odd co-rank. So this actually, the difference actually is because, so as proved by Brandon, for ordinary metric rank loci and a skew symmetric matrix rank loci, if you look at the derived category of the previous sheaf of constructive functions, the equivalent representation of A type, but for symmetrical case, the equivalent representations are of B type. So that's the difference between the two types of matrix rank loci. And also due to original definition of McPherson, 0 means that you can actually extend the distance one form of the natural block of such matrix rank loci, which would be interesting to explain from topology that why such objects have such interesting topological information. Okay, so here we propose an example to illustrate our algorithm. So we consider symmetrical 3x3 rank loci. So the corank 1 matrix is a hypersurface, and is actually due to corank 2 matrix rank loci. And the tau S321 S1 has two objects itself and also at tau 32. So they are of dimension 7 and 4 respectively. And following the Schubert calculus, we can compute out these Chen-Schwarz-Meffin classes as follows. And also you can, by plugging h by -1 and take a sign, you can compute the SM invariance. They are both 1. So we follow the algorithm here. You can see that we set up the corresponding linear system. So in this case, you take the tau SM310 by this polynomial above, and then this polynomial by the corresponding polynomial above. And then if you expand those two polynomials, the three polynomials, and if you look at the coefficients, this gives you a unique solution here, that the x equals 0 is a unique solution. So this actually tells you that Euler abstraction of sigma 3(1) at sigma 3(2) is 0. And then if you want to look at Euler abstraction of sigma 3(1) at 0, you would apply the Brasselet-Leucière formula. This gives you 1. And this actually matches our previous result on local obstructions. You can see that when k is odd, m is even, this is 0. Otherwise, it is just half of n and half of k. Okay. So, at last, we mentioned here that based on knowledge of the Chen-Schwarz-Meffin classes by the Schubert calculus, and also based on knowledge of the local obstructions of rank loci, we can compute the following invariants. So first, we can compute the Euler characteristic of the intersection of all three types of rank loci with any given hyperplane. So for generic hyperplane, the information are given by the Chen-Schwarz-Meffin classes, but actually we can compute the Euler characteristic with any given hyperplane. And then we can compute the stock Euler characteristics of the intersection cohomology sheaf complex of all three types of rank loci, based on knowledge of the micro-local indices and our local obstructions. And also, we can prove from purely algebraic point of view the Milnor classes and the local cycles for the what we call the homogeneous essentially isolated determinant hypersurface, which means that it's a transverse map from a projective space to the space of matrices. And the transverse means that the pullback preserves the codimensions. And we can compute the Milnor classes, which means that we know the Euler characteristic of the local Milnor fibrations. And then we can also compute local cycles, which is equivalent to the topological type of the local Milnor fibers of such hypersurfaces. Okay, so I will stop here, and thanks all for coming and listening. And also, again, I would like to thank the organizers and thank Professor Maria Ross for the invitation. Okay, bye-bye, and have a good day.